Okay, moving on to the AR model. Short for the autoregressive model, we have these different coefficients compared to the MA model, where I said there were a slanted phi. I think from ChatGPT, it still said it's called a phi, so that's what I'll call it. Notice how in the AR model we have variables that represent past values of itself. And so that looks a little more familiar to our last series where we regress time series variables. And so that's kind of what we're doing here. We're regressing variables based off its past, where compared to the MA model where we're regressing the errors. And that's probably what I should have mentioned in the last video, but yeah, so AR model concerned with the representing past values of itself, and the MA model concerned with the errors. And because AR models are modeling the coefficients of its past values opposed to its errors, we will have more significant or bigger absolute values of coefficients generally. And so the MA model, in its name, the moving average, is very mean reverting. So you can kind of see that there's not a very clear trend and very just very pretty consistent in where it's going, whereas the AR model, not a clear trend, but we definitely see up and down movements over time. Actually, one last thing I want to say is, for the order of the MA model, we represent the number by Q, and for the AR, we represent it by P. And so for autoregressive models where we represent variables, past variables to its current one, then we'll usually use P. And AR is usually more common, so. All right. Very similarly to the MA model, the AR model, we can kind of notice or find that it's an AR model based on the ACF and PACF. Besides visually it's also pretty clear, but based on the ACF and PACF, kind of the analysis part, if there's a decaying oscillation in the ACF, and then there's just one big spike in the PACF, then it'll more times than not, it'll be an AR model. Remember that MA model, this is flipped around. So PACF, there's like a slow oscillation decrease, and then the ACF, there's a big spike. And so the PACF or the AR model is just flipped around. All right. And just like the MA model, as our this should be order, but as our order increases, we have a slower decay. Or no, this is different. So as our coefficient increases, so the bigger our coefficient is within our variables, that means there's more autocorrelation, and so it takes longer for our ACF to decay to 0 because there is more correlation. Intuitively, it makes sense. So. All right, like the MA model, our autoregressive model needs to be covariance stationary so that it is less than 1. So both needs to be, in order for them to be invertible, to be switched to each other, the coefficients need to be added up so that where they're less than 1, the absolute value. All right, I'm gonna ignore this algebraic, these expressions. This is kind of where we get the foundations of yeah, I don't really know what I was intending here, but basically I think this is kind of the proof of why there's a slower decay when the phi increases. Oh, it's for this latter one. Okay. So when we notice the relationship between like the mu and the phi, And so as we add up more, as we add more lag values, and so we add up more fees, then the mu will actually increase, because this is going closer to 1, or this is going farther away from 1, because it's we're subtracting more values from 1. So this part's getting smaller, and so this overall value is getting bigger. And so when we add more lags, then it means it's more mean reverting, because remember that when we have an order of 1, that's when we have the highest coefficient, highest autocorrelation. So that's when the data will be the most clearly trending. But as we add more lag values, which we're doing here, that's when we have more mean reverting and less correlated plots. And when there is a clear trend, that means the coefficients are not, the model is not invertible. So when two path values equal to 1 or more, then we can't mean revert, and so we can't represent this AR and MA model into like a model when there's a clear trend. This is kind of like what I said earlier, where the AR model has, when we look at the analysis autocorrelation function, partial autocorrelation function, we have a significant spike. This is actually kind of wrong. I should probably fix this later, but ignore kind of this. There's usually one. Oh wait, no, this is an AR2. Okay, that makes sense. So yeah, 2 big spikes in the PACF. If it's an AR3, then 3 big spikes. AR1, 1 big spike, and then a gradual decrease in the ACF. MA2 model, this would be the PACF, this would be the ACF. All right, so I think that's pretty straightforward. A lot of times it's not obvious, which is why in the next video I'm going to go over the ARMA model. But before that, let's finish this part. Alright, so I said that AR models have more uncertainty because they utilize less volatile data, and they depend on past values, not errors. So this part is true. Is this part true? I mean, I assume so because I wrote it down, but AR models have more uncertainty because, right, okay. So like the MA model, they are very mean reverting, right? So we know that they're going to be closer to mean, whereas AR models, because they are more fluctuational, I'm not sure if that's a word, but because they have higher correlation and they're more they have more noticeable trends, we have very high confidence intervals because we're less certain on where these forecasted values are going to move compared to the MA model, where we kind of know, looking back here, we kind of know that they're going to be around the mean. Alright, that's it for the analyzing cycles. In the next video, I'm going over the ARMA model, which kind of combines this AR and MA model into one, because sometimes it's not very clear on which model we're going to use. Alright, but that's it for this video.